Alright, now we're going to go through part B of our Excel tutorial, and this one actually is a little bit simpler in some ways, but it's very critical to go over in terms of its relevance to our biochemistry lab this semester. And that is using a spreadsheet to generate a standard curve. Now I'm not going to go through all the background on this. I expect you to read it and understand it, but I am going to go through how to plot a standard curve similar to the kind, basically using data of the format that's in our example in the worksheet. Okay, so here I've entered into my spreadsheet my molecular weight data. It has units of kilodaltons, and it's always very important to keep track of those, even though I don't put them down here with the numbers themselves. And so I have a series of proteins that have these sizes, and distances were measured on the gel for each of those sizes, and you can see this larger ones, larger size proteins move the smaller distance all the way down to a larger distance for the small size protein. Now, we don't plot directly the molecular weight to the distance because there's not a linear relationship. We won't get a line. However, there is a logarithmic relationship between these guys, and so what we do is we can plot the log of this versus this. So first thing we need to do is calculate the log. So let's go in using our formula, log, and we're going to just do log base 10. And so we just click here, close parentheses, we get log base 10, and then we just take that cell, we drag the formula down, and we'll get basically the log of the molecular weight versus the distance. Now, we want to plot this, so what we're going to do is we're going to select the data that we want to plot, and we come up and we go to Insert, and we're going to go Insert and over here are the types of plots that we can put in under charts, and we're going to do an XY scatter with no lines connecting only the markers. So if we do that, then we'll immediately get up our little plot over here to the side, and what we want out of this, so this is actually a plot of one versus the other, basically the log of the molecular weight versus, or I'm sorry, the log of the molecular weight down here versus the distance traveled. So that's the form of our plot. Well, we need to put labels on this. And so what we should then do is go in to Layout, and under Layout we will want to, we can put a chart title, we can put axis titles, and I would go ahead and put your primary horizontal axis title, put it down here, and usually, well, and always what you want to do is you want to put not only what it is, but the units of it if there are units. So here would be log of the molecular weight, we put this way, and then in parentheses we'll put kilodaltons, so we know that those are the units. Then we can come up here and we can go for the vertical title, the vertical axis, and so if we do that and we have the title displayed rotated, you can select on this, and we click on here and basically delete that. This is distance in millimeters, we put in parentheses. So we always want to label our plot. Then we could put a title for the entire chart if we want to. We have different options for that. We could do it above the chart, which I tend to prefer, and then we'll just call this our standard curve. And usually you want to be a little more creative that tells you what it's a standard curve for. Standard curve for, say it could be a particular experiment. I'm going to say for Excel tutorial, but you want to have some explanation. You might even put a date in here or anything like that. Annotations of your chart are very important. Now we only have one series here, so that's not significant to have the legend here, so sometimes I'll just delete it so that we get it out of the way. You can also adjust your axis, So if you click on an axis, it'll let you select the options for it. I want to make it so that my axis is closer to my data. My data fills the curve, so I might make that x-axis have a minimum of, let's say, 0.5 rather than 0. So I might make the minimum fixed at, and I could do, other than 0.5, I could do 0.75. And then that adjusts the bottoms, pulls that axis over here, so it puts the data more central and fills up the curve a little better. Now, the next thing that I need to do is I want to add a trend line. So if I click on the data here, you can see the data. I can come up here and I can add a trend line. Now, I want to do a linear trend line, even though this is not a linear set of data for the molecular weight. It is linear for the log of the molecular weight versus the distance. So I still want linear trend line. I put that in there, and then I can, oh, and actually one of the things I wanted to do was come down to options, and I want to, actually under more trend line options, I want to tell it to display the equation on the chart, and I also like to see this R-square value because it tells me how good the fit is. The closer the value is to 1, the better the fit. And since this is an ideal set of data, the value is actually right at 1, so the fit of the line to the data is perfect. Now what we get from here is we get the slope, which is -20, and we get the y-intercept, which is 50 here. Okay, basically meaning it will intersect the axis at 50, and the slope going downward is -20. I'd also like to show you, basically remind you in essence of how to use the information you get from a standard curve. But let's say, for example, that you were told that you had an unknown protein that had traveled, say, 22 millimeters on a gel. So if we have an unknown protein that's traveled 22 millimeters, then we can calculate the y for that, or I'm sorry, we can calculate, we've got basically 22 is our distance, so that is y. We could calculate the x value for that actually in a very simple fashion. So what we do is we take this equation and we would have to solve it for x, because this is if y was 22, then what is x? Okay, well if we plug in 22 for y, then x is going to equal to, it's going to equal to basically y, this value here, minus 50, because we've got 50 over here. Okay, so we're going to subtract 50 from both sides. So we have y minus 50, and then we're going to divide by minus 20. So we would need to parentheses this entire thing, right? So we put a parentheses here, here, and divide by minus 20 for this example. Now, there's one thing, what we'll get is we will get a y value of 1.4. Now, is that the size? Or I'm sorry, x value, is that the size? No, because x is log of molecular weight. So to get the molecular weight, we need to get the inverse log. Now, if you do this on your calculator, you can just take the inverse log, and it's assumed to be base 10. But another way to do this, if you're doing it in Excel, and don't believe there's an inverse log function. Yeah. Oh wait, there's a log inverse function here. Okay. That's not the function that we want to use. Okay. This must be something, it looks like it uses some other thing. This is not the function we want to use. So what you would do is, this one is actually fairly simple, because if you have the log of something, so like let's say for example, let me just do this kind of off to the side here. Let's clear that out. Let's say you have x is equal to log of y. Okay, then based on the rules that will govern logs, you can calculate what, if you know what x is, you can calculate what y is in the following fashion. So if I know what x is, I can figure out y by taking both sides of the equation and raising 10 to the power of that side. So basically 10 to the x is equal to 10 to the log of y. And 10 to the log of y is simply y. So 10 raised to the log of y, and here we're using log base 10, is simply y itself. Okay, so what does this mean? Well, this basically means that we've got y equals to 10 raised to the x power. Okay, so 10 to the x power is y. So if we come back over here, we can then calculate the molecular weight. We can figure out what y is by basically taking equal sign 10 caret is the symbol for exponent, or that's shift 6, and then we basically just click on x here, and if we hit enter, we'll get 25.11 kilodaltons, or 12 kilodaltons. And does that make sense? Well, yeah, if you come in here and you look and you say, oh look, 22 would be just a little bit smaller than this, and 22 would be very close to 26, and so this does make sense. 25 kilodaltons for 22 millimeters of distance travel. So that's how we would use this standard curve in an actual calculation.